Okay, welcome and thank you for joining this second Surface Ventures webinar. So before we go any further, can I check that people can actually see me and hear me? And again, to test this as last time, can you please write where you are joining from today in your chat box on your right? Okay, so we have UK, we have Canada, Austria, Portugal, Sweden, Isle of Man. Great, great. Saudi Arabia, USA. Excellent, great. Thank you for that. So it seems that everything works, which is great. Many great places there, and I hope that the weather is nice where you are joining from today. Certainly very nice today in the UK. 28 degrees in Leeds right now, which is the hottest day so far. Anyway, my name is Tomasz Liskiewicz. I'm a director of Surface Ventures, and I'm your host today for today's webinar with Professor Andrzej Wojewodin. Andrzej is a professor in the Department of Materials and Engineering and Associate Dean for Research in College of Engineering at the University of North Texas. He holds Diploma of Metallurgy Engineer and PhD in Material Science, both degrees from Tula State University in Russia. In 1993-94, Andrzej was a UK Royal Society Research Fellow at the University of Hull. From 94 to 2015, Andrzej worked in the US Air Force Research Laboratory, leading tribology, thermal management, nanoelectronics, and material research teams. He joined the University of North Texas in 2015, where he continues his research in surface engineering, films, tribology, electronic materials, and adaptive manufacturing. Professor Andrzej Wojewodin has over 300 technical publications, published book, and 8 book chapters, and has 12 patents and innovations to his name. So we are very, very fortunate to have Andrzej today with us. In terms of agenda, we'll start in a minute with Andrzej's presentation. Then we will switch for a few minutes to Adrian Harris from our sponsor, Micromaterials. And then we'll come back to Andrzej for your questions. And we are planning around 60 minutes in total today. Before we move on, let me say just a few words about Surface Ventures. We are a non-for-profit organization, and our mission is to provide world-class surface engineering education for academia and industry. So every month, we will bring you a sector-leading speaker to present the current challenges and future trends in surface engineering, very much like today. We would like to learn a little bit about you, about your audience. So I just shared a very simple poll there. So can you please answer the question which should pop up on your screen? The same question as last time. Are you from industry or academia? And I appreciate that a few of you will represent both industry and academia. So feel free to pick any answer in that case. Okay, so answers are coming in. Okay, so it looks like around 75% attendees from academia and 24 from industry. Very similar to last month. So perhaps I can stop asking that question and come up with something else for next time. Okay, thank you for sharing. So now I would like to hand over finally to our today's speaker, Professor Andrzej Wojewodin. Andrzej, over to you.
Hello, everybody. It's kind of interesting times now that we are connecting instead of person, we're connecting all through the computers and through all those wonderful interfaces which we have. So it is, of course, a pleasure to meet you virtually, and I look forward when we can meet all in person. I wanted to say good morning because I'm in Texas. It's 8 a.m. in the morning, but I would rather say good day to everyone, so that the people in the UK and in Asia and all other places will take that good day correspondingly to the time you are now. Yes, I've tried to bring today some ideas about adaptive tribology and its surfaces and interfaces. Hope to answer some of the questions. And this is really the discussions and dialogue from my perspective about some of the concept of adaptive lubrication. Before the start, I'd like to thank the organizers who are hosting the sessions, and Thomas for working out and organizing these wonderful sessions of the engineering, which we can all enjoy in here. With this much, let me start. I will share my screen, so I will disappear maybe from your big cameras, and on the background, I will see my charts, and I will come back in the end, as Thomas just said, to answer the questions. Okay. You should be now able to see my screens in here. And this is the title of the talk, coming from the Texas, so just a little point in there. Let me move that box out of the way. Just the point at where we are. And this is just giving an idea why it is called University of North Texas, because we're actually in the north, but not let's get north get confused for you. It is starting getting fairly hot in here. So we're in the 90s Fahrenheit, not getting triple digits, but coming to that. As my next charts, I would like to thank my co-authors on many of the publications which I'll be using in this talk today. And I put the pictures of some of the people around the globe I had the privilege to work with together. Many of them are my good friends, and we carry on through the life as well as through the professional engagements. My apology if I miss someone in here, but it's because you will see here that all the charts and presentations I show is the result of collaborative work with the people around the globe. My next chart is we'll talk about outline, and I kind of structure the talk today. We'll bring motivation, the concepts, and overall landscape of this adaptive mechanism, and try to position them versus the temperature for kind of sorting them a little bit in that regard. And then I'll go some examples, and I will do a little bit more detail on another composite coating just to highlight the mechanism. But then I will step out of the PVD processes and will show the examples of how we can use some other alternative technologies listed here: electrospark deposition, laser texturing, and some of the plasma electrolytic oxidation, how to achieve very similar adaptive behavior. So it is not just bounded to the PVD processes. So, and then hopefully I'll come back in time to the end of my talk. So starting with the motivation, why we need adaptive materials in tribology? Well, for people working in the industry, know this better than anyone. It is the machines have to operate on multiple operating environments. And aerospace, of course, can be extreme. But in a tool industry, in an automotive, we always encounter the condition when you have to operate across the multiple temperature ranges, multiple environments, high and low humidities, maybe some gases, as well as the loads and the speeds conditions, which just leads to the challenge that how you pick up the best tribological material, and specifically I will be focusing on the solid lubrication. So when there's not liquid is available, maybe the high temperature and or some others, how you pick up the material. And I like to use this chart shown in here, just kind of highlight that they have major groups of here, and this is just examples. And I like to use the chart because it's very clearly positioning that there's no one material which can work adequately well for any one of these environments. And I kind of put in them humid air, dry nitrogen, and vacuum, 500 DC air. So I'll take a molybdenum disulfate, an example, great for the vacuum and dry nitrogen, very low friction, long endurance. As soon as you go to 350 C in air, it's oxidizing and it's failing. And then so it's and then the story repeats for any other material shown in here. And then we of course have a group of hard coatings which are good and wear resistant, friction coefficient are high. So we like to be in here. And the answer is normally, okay, well, let's combine this together so they can work. And the trick is then to make sure that on the surface during the work you have the right material, which has come to that chameleon concept, which is I was working with my colleagues for many of the years trying to advocate. That's what the idea is for adaptive lubrication. Basically, we want to engineer our coatings and our friction pair. So sometimes we also need consideration of counterpart and environment, so that in any conditions, the reactions going on, and this reaction can be temperature induced or friction induced, that reaction will end up in the favorite material for the lubrication. So that's basically we have the lowest friction material possible in a wet track in any of the condition. And if the condition change, we would like our material adapt and basically change the surface in terms of chemistry and composition and structure, so we have the right material that can have a low friction. All right, so this is kind of concept. Okay, how we can do that? Well, we need to come out with the mechanism, how the materials can adapt and what type of the things which we can use. So over the years, multiple mechanisms came out. And I'm sorting them out in his table. And the table is going by the temperature column here, going from a low temperature all the way to 1000 C. And I will go through that talk today just using some example after this group. And we'll talk about hexagonal solids, such as transitional metal dichalcogenides and evolutions in there. I probably, because of the time, I will skip that fullerene and some other closed shell structures, which can buy additional 100 C, perhaps because of the closed edges. I will highlight use of the metal, which is relies on softening and diffusions, and highlight also the high temperature end on the oxides, where you have specifically look on Magnelli phases and some other binary oxides for the lubrication. And those are the mechanisms which is complete adaptation. And we can talk about how we realize them using different techniques. All right, so let's talk about the first group on the technologies, nano-composite coatings using the PVD. And I will use it to highlight some of this mechanism before I show also some other examples. One of the first success which we had in a group developing this type of materials is targeting the environmental change between humid and ambient condition. We have oxygen and air present to the dry and vacuum condition. So you can think about it because between the Earth and say the satellite use. So the people who design the satellites always need something like this because you test on the ground first, and then once you launch, you operate in a vacuum environment. So you have at least one cycle, sometimes more, because depending how you test those things. So one of the materials which we work on that time is combining the hard phases based on the carbides with the carbon material such as DLC or fluorinated carbon for the lubrication in humid environment. And then we can also add molybdenum disulfate and tungsten disulfate for the lubrication vacuum environment. And it worked fairly well. I'll show you the example. The challenge was how to get it to the high temperature. What if you also need to temperature cycling or the temperature rise? And this is fairly challenging now because we involved oxides formations and unrecoverable reactions in the surface. So you need to start thinking about those things. In all of those designs, it is very crucial, and this is something I want to highlight, that it's very crucial that you not only think about what's happening in here by the chameleon adaptation, but you need to have this adequate load support because you want to have your tribo film always very thin and laying down on a hard supporting layer. And this is something which we all know from tribology books. And for many years, people such as Alan Matthews and Ken Kalbrink, and they were advocating for this type of surface engineering. And don't forget about that adhesion, because if nothing sticks to the substrate, especially when you do the temperature cycling, that's not going to work. So, and it's from practical perspective, industrial forks, okay, the very first question always asked to the coating manufacturer, how well it's adhered. So that adhesion is critical, so you want to engineer good interface, bonding, etc. I will not focus today on engineering and stress equalization, etc., because it will be completely different talk and it will take me the full hour to do that. I will focus on the tribo film here, but just make sure that in all conditions that thing was also thought of. All right, so let me move them here. So that's to make those materials and the composites and the PVD coatings. We use a number of the techniques, and I'm showing them in here on this chart because those are given an example of some of these PVD tools we have available to us. And I listed in here with this in blue highlight the energies of the deposited fluxes incoming. And this is something which is we using in a PVD to our advantage. The reason is when we combine these multiple materials together, we need to have, just based on thermodynamics, their energies of the formation is different. So if we only rely on the substrate temperature, we run into a big problem that some of the materials require high temperature synthesis, such as carbides or some of those oxides I will show. And others cannot tolerate the high temperature. So carbon-based materials or some degree like chalcogenides will require maybe a reduced temperature. So to overcome that, we're using these high energy fluxes and these techniques. And this is, for example, in the magnetron sputtering option, you can have a regular one, or you can have a high PIMS option, and you can bump up by order of magnitude the energy of the incoming flux, which you then compensate for the low temperature, and you drive the formation of the normally the high temperature phases and reduced temperatures. All right, so that's me the moves on in here. So in example, so we want to combine this here, and one of the example which I've worked in before is a combination of, in this example, sputtering and pulse laser deposition. You see the movie coming here, the laser striking on the bottom, and the plume is coming up, and the sputtering is on the sides in here. And out of this arrangement, we have a combination of relatively high energy flux coming of the target, and target is zirconia oxide, molybdenum disulfide, and graphite, and then relatively low energy flux coming from the magnetron. In this case, it's providing gold as the component of this coating. Of course, in that movie what you're showing here, you can have also multiple magnetrons replace the PLD with the arc evaporation source and have all the different combinations available, and that's our use in fact. But let me move it, okay, what these materials can do. Well, it comes to this type of the structure because this is an example of zirconia oxide, gold molybdenum disulfide DLC coating. And on the left is a TEM image. On the right is the schematic, what's going on inside of the structure. The dark grains are the zirconium oxide grains, which provide the hardness and wear support. You have incorporation of molybdenum disulfates. In the matrix, you have amorphous YZ, which is not fully crystalline. You have also carbon sitting there, and you have also inclusions of the gold. And gold sometimes it sits in interstitials in the positions in a zirconia oxide, and sometimes it's sitting as its own crystalline phase. All the phases here, the nano-crystalline, as you can see here from diffraction rings. And this scanner is the design for this material, which can ready to adapt and work in multiple environments. I will show over the presentation some example of that. But first, let me focus on a low temperature performance of these adaptive coatings. And that's in this regard, let's see the mechanism which we can using at 300 C. And here and below. So like here we talk about the chalcogenides and graphite. Perhaps hexagonal boron nitride is a sort of exception because it can go to the much higher temperatures. But let's focus on this thing and what's the mechanisms there. And when we know from a practice perspective, when we do this type of adaptive coatings or lubrication with this material, we can achieve a very low friction coefficient. This example, tungsten carbide DLC WS2 chameleon coating, which has carbides as a hard matrix DLCs for the humid environment, lubrication WS2 for the vacuum. So that's here shown here is a vacuum test. We have over 2 million sliding cycles, so it's very long test. And as you can see here, the friction is actually dropping down, and there is no way to show that it's going to fail. In fact, it will run forever because once it's developing the tribo film and supporting, the wear pretty much dropping down to non-existent. Okay, what's happening in terms of mechanism? Well, there is a tribo film formation. And this is from our results in here, but I also have that confirmation from other research groups. And this is the group from Dmitry Shtansky and Moscow Steel and Alloy Institute. And they are working on titanium chrome boron nitride matrix with a tungsten diselenite addition. And the similar results, you have very low friction coefficient. And when looking at the films in here, you see the transfer film, and you can start forming this lubrication. When you look on a film in the cross section, it is fairly looking glassy-like. Perhaps some crystalline or nano-crystalline you can detect in here, but mostly amorphous and very dense films in here, which will develop then the transfer film, which provides lubrication. All right, so let's look on the transfer film in much more zoom vision. So we're looking in here in the cross-section of the wet track in reciprocating sliding for the moly tungsten sulfur selenide coating up to 10,000 sliding cycles, and the friction was stopped. And then we're looking right on the counter here through transmission electron microscopy. You can go to the brilliant work by Jingjian Hu in tribology letters who was explaining how using the FIB and TEM he was able to do that. But what we see here immediately, right under the silicon carbide, which is amorphous pin, we have right this here, the basic planes oriented parallel to the surface. And you can see here they're very thin. You notice here there's 5 nanometers. In fact, we can go zoom in and can count, and we can count how many basic planes it takes, and we can see 1, 2, 3, 4, 5, maybe 6. So with this, all we need to have just few 5, 8 atomic layers will do all the work. And it's over 10,000 sliding cycles. And after that, it's pretty much, there's no wear because the reorientations of the randomly oriented grains and that location and the amorphous grains took into the crystalline hexagonal phase in here. And this is the adaptive mechanism for that calcium solid, which is well known. And this is here is the confirmation of how you can see it in real life. All right, but let me move in here to some demonstration how this gets used. So one of the very interesting and cool tests we did with University of Florida, Greg Sawyer, Brandon Crick, and others, and Tribologics, who provided some of these coatings. Air Force Research Laboratory was, in that time, I was working with them, and we were doing the experiment for the MISSI on the space station. And it was, to our knowledge, it was the only one tribological in-situ test performed in orbit. What you see here is actually tribometers made in boxes, which should put in the boxes, then the astronauts take out, put the boxes outside of the space station, in front and in the back, and then so the different exposure, and left along there when the tribometers was working and telemetering the data back to the ground, so we can see what is the friction coefficient going on in situ once it is going around the globe. And it was in orbit for this duration, a little bit longer than we expected. And when this came back, we had an ability to analyze and compare before the flight and after the flight. And we have a number of coatings there, including this chameleon coatings are shown in here. And the chameleon coating shown excellent across this space test. And therefore, that was one of the things which is always answered the engineers in aerospace, was it flown in space? And we can answer, yes, it was flown in space. It is shown very good as a comparison to some of the baselines, and this is how to get the space qualified. And Brandon Crick was presenting the World Tribology Congress in 2013 these results. Let me move in here to the 300-500 degrees C range now in the mechanism, and we talk about here metals, because now the chalcogenide will be oxidizing, and they're not really get survive in this type of temperatures. As I already mentioned, maybe fullerene structure can extend it, but you're talking in general, we now have to use some different mechanisms. One of the mechanisms we can use is gold and silver encapsulated in the matrices. So those are interesting then concept, because if you take one of these temperature stable oxides, such as zirconium oxide, or you can use the nitrides, I'll show you an example of nitrides too, and put the soft metals there, and put them into distributed, like between the grain boundaries, or even in a crystal lattice, defective crystal lattice itself. And once you heat it, they will driven by the surface energies minimization out of these oxides to the surface, and they will coalesce on the surface. And now they're coming, and because they're soft, and because the temperature is now more than 300 C, they're more softened, they provide a good lubrication in that condition. So kind of show you the examples in here is with the zirconium oxide and gold, and pardon here, this is the gold, should be the silver. So you can see here the gold part, gold grains are showing up on the surface, and they are smeared, of course, in a tribological track and provide this lubrication shown over here. So that concept is equally applied if you replace the zirconia for different matrix and you replace gold for silver. And this is, for example, a work by Dmitry Stansky again from the Moscow Institute of Steel and Alloys, where they're using polycarbonate nitride now coating and the silver as addition. And you can see here right around 400 C, the mechanism get triggered, and you can see the silver coming up on the surfaces and provides the friction reduction. Very similar as shown in the previous chart. So it's working very nicely from that perspective. The problem with that mechanism is that it's diffusing sometimes too fast, especially as you start increasing temperature, say the 500 C. The diffusion is so fast that all the materials get depleted very quickly on the surface. So one of the ways to do that, well, put a diffusion barrier layer, such as titanium nitride, and it will restrict the diffusion. And just doing this thing, just putting titanium nitride diffusion barrier layer and do nothing more to that, split it in half, we have an extension of the wear life for many thousands more sliding cycles, because it restricts the diffusion towards just the wear track which is needed using subsurface diffusions mechanism here. All right, so now we did this. Of course, you can also do more engineering. You get more of these layers, diffusion barrier separation, and now you can start talking about thermal cycling, or at least few thermal cyclings available to do that, and try to maintain the friction coefficient in low once you go between, this is case 500 and 25 C through this adaptive mechanism. Now we're covering like low temperature and the mid temperature. Now let's go to the high temperature. If we go to the higher than 500 C, that silver will get out very quick, and even with diffusion barriers, and we need to have something else. And now we're moving to the world of the oxides. At 500 C in the air, the chalcogenides or carbon, or even the soft metals, which has become too soft to work, so it's become not very enduring mechanism. So we need to have the oxide-based chemistry working, because then we don't fighting the nature, oxide naturally form. So the trick is how we can guide this oxide formation to the ones which we need. Okay, which one we need? Well, we want to have which are stable in this temperature and have low friction. So meaning low shear or low shear modulus oxides. In Magnelli phases or defective oxides like tungsten, pentoxide, moly, trioxide, some of the listed here, is one of those, of course, the choices. And people working in the tool industry well know that's the benefit of the addition of the vanadium to the hard coatings from that perspective. And then you can look on a double oxide, which can help to reduce the temperature at which the mechanisms get tripped. And here we also can rely on a modeling tool to help us, because that material domain space became very large in here very quickly, with the multiple transition metals and oxide structures being available. And now you're adding double oxides, which is extends even further. So what we can do, this is the work from my good collaborator and friend in Aachen, Jochen Schneider, who working with Tom Transwinkel and Dennis Music. And we did in 2010 the calculations of some of these double oxides, trying to locate the low shear modulus directions in these oxides, which will lead to the lubrication. And we look at the electron density populations and trying to identify where this electron density population is less, along which planes, which can then lead to the calculations of the cohesive energy, leading to the shear modulus estimations, and understanding which one can provide lubrication. So the results are showing on us here. And then graph shows, for example, that energy for that the cohesion energy, and the C144, basically you think about all the shear modulus on the left, on the right here, the cohesion on the left. And this is a different oxides which you run, and the winner is in here in terms of lowest possible shear modulus is a vanadium pentoxide. Okay, well, we already know that from the tool industry. But this is kind of showed us that, yes, we can use these tools, and we can look on all other mechanisms here and predict it. And to take it further, because that was 2010, this was went further down, and this is work coming out of another my good friend and collaborator for a long time, Dr. Samir Audi, who is in University of North Texas, working with me then here. And he is also working a very brilliant grad student now. She is very brilliant engineer in General Electric, Darcy Stone. And they look on a double oxide. So the silver vanadate is one example here, silver molybdates. Do the calculations, look on energies and electron distributions. They look also on where the metallic bonding is existing rather than covalent ionic bonding, so you can identify this type of oxides. So one of this silver vanadate came out as one of the winners, and then experiments were set to track it. The problem was to track it that this is forming at a fairly high temperature, and at moderate temperature is forming different oxide. So we need to have also a tool to be able to detect it. And then with Dr. Chris Muratori, who's now University of Dayton, and that time we worked together in the Air Force Research Lab, and we look into the design of the in-situ thermometer. We have a brilliant engineers helping out. John Bolton was one of them. And we constructed Unico machine, which is in-situ Raman for the very high temperature. And you're talking about 1,000 degrees C in here, and bringing in the probe all the way in, keeping it optically intact, meaning no distortion when you're ramping the temperature up and down, taking the signal out of the fiber optic to Raynishan Raman, and now we have an option to look on a track as we spin, so we don't stop the spinning, and as we heat, so we don't stop the heating either. So with this thing, we can look on what type of oxide we're forming on our surfaces. And to my knowledge, this is the only type of the apparatus was constructed. It is now rebuilt in the University of North Texas. We're using it. I'll show you some other examples. But going back to the silver vanadate, you'll see that here as we're ramping up the temperature, and and this is the sample temperature curve, and we go all the way to the 700 C in this case. And right on the green point here, we commit the test, and we start the test and start looking on oxides, and we are particularly tracking the formation of the silver vanadate, which will start appearing in here through the peaks developed. And then we now have the answer why the friction is low. There's the friction trace in here because we do have this double oxide. When we cool it down, and this is here, when we cool it down and we do the post-mortem analysis, kind of room temperature, that peak here is get masked by some other oxide, like you see here, a vanadium pentoxide is showing up in here. So it is not a clear identifiable. There's another oxide showing also here, as you can see in in-situ. So in-situ is very clear presence. So this is the power of this technique because it tells us exactly at this temperature, and then not leaving any gases after you cooling because you form different oxide. All right, so I show you 300 C moderate temperature and about 500 C. Can we combine this all together? Yes, we can. And now this has come back to the structure which we have: zirconium oxides, silver, moly, molybdenum disulfate. This is the data points, different temperature, room temperature, 300 C, 500 C, 700 C, And the different mechanism, different temperatures we discussed, but it keeps the friction right in a bay at this point than here. So it is working, and I think I'm done here talking about some of that PVD coatings. I want to switch to different highlights and different engineering materials. All right, so let's show that we can also do such adaptive coatings with other methods. So we're not just bound to the PVD. So PVD is a great option. I like it, and I worked for many years with that. But there is also other alternatives which may provide also sometimes even better on different perspective. So for example, metallurgically bonded electrospark deposition technique from composite coatings. This is very rapidly coming up method. And this is from Professor Evgeny Levashov, as also in the MISIS, who are using self-propagating high-temperature synthesis to synthesize a number of the composite targets and materials and electrodes. And you can see here some of them, just some of them. And the list is just continuing in here, growing. Every year they develop multiples of the thing in here. And a part of this technique, and it's a self-propagating synthesis shown in here, that you can actually combine very high temperature materials together in a dense electrodes and a dense materials, and you can use them then for making the coatings. One of the techniques which can be used, for example, is electrospark deposition, and be more exact, pulsate electrospark deposition. For those who are not maybe that familiar well, it takes the electrodes, which is made out of one of these composite materials which you just saw, brings to the working part. In this case, there's one of the shafts, and then by applying the high energy pulses with a high current and regulating these pulses, as well as sometimes you also adding mechanical motion of the electrode, you can very quickly build a thick metallurgically bonding hard coating on the surface, as shown right over here. And advantage is that you're transferring the very large materials of the materials and you bonded it metallurgically to the coating. So you're solving this adhesion problem, as we talked, right in the beginning. It's in principle of this process to have. With that, you can now move to make this type of adaptive materials when you also can engineer a very great supporting base. And this is the example of some educational technology, what you call a chemical reaction-assisted pulsate electrospark deposition. And using those different electrodes, now talking about strengthening titanium alloy, you can drive cross formation of titanium tungsten carbide, and with some of the ductility ended through titanium tungsten, so you have very well metallurgically bonded and hard supporting base. And you can finish out with a material which contains carbon. And the carbon is there for the lubrication. And the effect, you can see it by itself. Friction coefficient without addition carbon, friction coefficient with addition carbon drops right down there. And that is one of the powerful methods to move towards this adaptive coatings formation. I hope that in the future we also see electrodes with the tungsten disulfates and some others, so we can also have other lubricants be produced by that method. This is up and coming method in being developed. You can find more of this works listed on these charts. But let me move it further. Another example I want to highlight is, okay, can we use some other methods? Laser texturing is another popular method where you can modify the surface to provide them a different morphology, and we can use it to create reservoirs for the solid lubricants. It's very simple. You take any of the hard coating, in this case we're using titanium carbon nitride, and then you do the laser drilling with the high-speed motion stage and a pulse laser, and in a matter of a few minutes you can engineer something like this. We have a bunch of the dimples created on the surface, which will serve them as reservoirs, and you can control the diameter and the depth of these dimples. Now we put this chameleon coatings on the surface, and it's based on carbon, molybdenum disulfate, and antimony. There's a chameleon coating that was developed by Jeff Zabinski, Andy Carrini both, and Tribo-Logics. I had a chance to work with them on this thing, and we combine in here the laser texturing and this chameleon coating, and we're running it here in humid and dry. You can see they have the dimples, and you can see the partial coverage of these dimples in here. Importantly, using the Raman techniques, we can confirm that in a humid environment, you have graphite has a lubrication here. Once you change the environment to the dry, you now start seeing molybdenum disulfate. The molybdenum disulfate will oxidize in humid, so it will start disappearing or diminishing here. And to confirm that is going back and forward, we have cyclic humidity tests, and here with the humidity go high, go low, and friction is recovering every time to that lubrication by molybdenum disulfate in the dry conditions, or lubrication by the graphite in the moist condition. And we are confirming with the Raman techniques, seeing that the actual adaptation had occurred. So working very nicely is in here, and then my industry partners, and this is the example from Tribologics, applied it. This is the gear, which is intended to work in low temperature cryogenic conditions. And you can see the dimpled surfaces on the gear surfaces, and then the coverage is in here, and that is working very nicely here for the turbo pumps. All right. Moving to the final one, and here I want to present, this is a thick oxide coating based on a porosity with embedded solid lubricants in here, and using plasma electrolytic oxidation as a process to create this. For those who are not familiar with the plasma electrolytic process oxidation, as a very quick overview, you need to have electrolytic bath, for which you put potassium silicate solutions containing you using the aluminum or titanium or some of this what we call weld materials to make a part, put it inside of electrolyte. You're using the high voltage pulses, and you break the electrolyte, so you initiate a micro arc sparking on the surface. So you can see the glowing in here, this micro arc. So then you have aluminum, say, from a part. You have silicon containing an electrolyte, and the result of that, you forming a very dense aluminum silicon oxide coating with the alpha alumina phases, gamma alumina phases, and some amorphous phases as a soup in there. Alexei Yerokhin in University of Manchester, and I had a chance of working with Alexei for many of the years, is one of the process development. He published several review papers on that, so I will draw it to your attention. And he was helping with some of these coatings, with this coating production using his technique. So Alexei is working with multiple sources which you can generate a different frequency. And the frequency is very important here for this particular process. This is the example from one of his work, where it has a low frequency of the 50 hertz will lead to the porous and a little bit thicker coating, but a well-developed morphology and developed porosity, especially in outer layers. And if you increase the frequency now at 2.5 kilohertz, then the materials became much denser and it has much less developed porosity. And regulating the frequency, then you can tune between dense material and porous materials, and this is what became attractive for adaptive lubrication. But before I go there, because this frequency is also into the audible range, so you can sort of hear them. When Alexei was working on this with his longtime collaborator, Evgeny Parfenov from Ufa Aviation Technical University, they're both a brilliant minds people, and they said, well, let's play around with the sound of frequencies. And as a demonstration, they made a very nice movie in here with a sound to that. I hope you can see it. I'm going to play it for you now in a moment. But that, all the sound is made by the process itself, by regulating the frequency during the process. And you can see and hear how the process works. Oops, sorry. Technical issues here. All right, so you can see that, and that what you saw is a part made out of this little yellow submarine with a corresponding tune to that. And you can find more in the works by Evgeny Parfenov and Alexei, and when you discuss in details how this frequency is can be used to monitor the process as well as to control the film densities and porosities. But meanwhile, let me move it in here. In our case, we're using this highly porous morphology, so we specifically tune the process to open these things, so we can use them as the reservoirs for adaptive lubricant. Those electrolytes and regimes for making the coatings, thus the well-developed roughness, which get resulted, and a coating again made out of alpha gamma aluminum and have also some silicates in there. Now, on the top of that coating, we burnish the chameleon composition, and it says burnishes in here, and it's nice and covering is through that. Well adhered. Of course, the roughness drops down because now it's all smeared on the surface. And now we come back to the testing those, and we tested first in a threading wear testing with reciprocated. And here's a calibration work done with Thomas Liskevich. And that time he was in Leeds University and has the machine where you can apply the load, and it's accused the reciprocated motion here. And we're looking on a stick slip transition. We also look on gross slip regimes when we have wear. So I'll show you some of the gross slip regimes in a moment. I just want to make sure that also to mention that yes, stick slip transition was also drastically reduced for this chameleon composition. But on a gross slip, if we have the plasma electrolytic oxidizing coating without any chameleon, the friction coefficient is high expected, is a hard, is a ceramic. As soon as you put it here on the top, the friction drops down very low. And this is against steel, and this is against aluminum. Of course, in dry nitrogen, it gets even lower and much more enduring because molybdenum disulfide kicks in and working in there. All right, so this is the room temperature. Most recently, and now we're showing the result from my lab here in the University of North Texas, where we have this in-situ Raman tool, which was developed originally in the Air Force Research Lab, now it's get reconstructed in UNT. And it's a very unique tool again. You can see here, you're looking right inside of this oven here where all the action is. And this is the loading pin, and this is the Raman probe, which is taken out. Agha Shirani is a brilliant graduate student, just about to graduate in here, working on those materials. And he was collecting during the friction run in here, as PAO and the graphite disulfide antimony chameleon composition at 300 C, and he collected the Raman spectrums every so often the cycles. And we can see the evolution of molybdenum disulfide, antimony trioxide, and also the graphite. Nothing really much changed on the graphite. It didn't seem to be showing much change. But we definitely could see that antimony trioxide was dropping down, but molybdenum disulfide was enhancing in some signal. So to quantify it, we kind of plotted the ratio of antimony trioxide to molybdenum disulfide, and we see that it's going down. These are two different tests, just to show that during the test is going down than here. So we have less of antimony trioxide presence and more molybdenum disulfide presence on the surface. So what's going on in here? Well, for answer that question, all we need to do is just go back to the literature 14 years ago. Jeff Zabinski was looking on these time chameleon cutting compositions, and there's right there working with this on the composition using transmission electron microscopy, looking on a post-mortem analysis, not in situ, but post-mortem analysis. They formulated this mechanism that antimony trioxide rotates and dislodges during the friction and moving downward when leaving more molybdenum disulfide surface rich on the surface. So 14 years later from that publication, we confirmed that mechanism shown in here. But there's more to the story, because we also see very interestingly that not only that antimony trioxide dropped down, but the wear rate and frictions is dropping down with the temperature. Normally we see a reverse. You increase the temperature, you have high wear rate. And that particular combination was kind of puzzled that the retroarc was actually dropping. Of course, we couldn't go more than 300 C. It's aluminum substrate here, right? So it started getting softer after that temperatures and heat to support the load. So the friction is dropping down very low, and we can say, okay, the friction dropped to ultra low 300 C because we think we're driving the moisture out, and therefore that molybdenum disulfate can slide very efficiently, almost like in dry conditions. But what's happening over wear? Why the wear is so low? So to answer that, we have to go back and do some cross-section analysis with the TM. And interestingly, what we've noticed that, and when the coating is made, and this is before running test, and the PO coating here, the chameleon on the top, this is platinum layer just to make the TM. You can see here the defects and cracks inside of the chameleon coating. Okay, we have open porosity in PO, and we certainly can expect some open pores not yet filled with chameleon. That's what we can see here. And then with drawing on the room temperature, we can still see them, right? But once we run on 300 C, that is get so much uniform. We don't see much of the porosity. I definitely don't see any cracks. So almost like a self-healing effect in here. So we think that at this temperature combination and pressure by the wear, we are forcing the chameleon composition inside of this porosity and cracks, and the materials actually become more denser, and therefore that provides better lubrication, more reduced wear. And I'm running out of time now, and I've got a few words on a summary, which I hope to give you a good overview of major concepts for the adaptive surfaces. The main ideas in here, and it's very straightforward. Need reservoirs filled with the temperature-sensitive environment reactive phases, and you want to put them in harsh and oxidation-resistant matrices. So always think about it, what you put in, and always think about what's environment is. So the reaction follow the direct way, the way to leading to low friction. Think about the low, strong bearing phases to support in all cases what you presented. That's all the basis work here to support this load, because tribofilm is very thin. Ideally, you want to have just few monolayer thin. Then you want to have a balance, hard and soft through all these coatings, because you always have abrasion, and this is normally so for the endurance. And finally, and this is because you want to put in practical application, the cost is matters. So performance with the cost, choose the technology which you like, thickness versus the finesse of the finishing. And here you can think about PVD, laser texturing, PO, PAD, some others, list is growing. And with that, thank you for your attention. I'm ready to take your questions.
Exciting research and excellent talk. Thank you for that. Much appreciated. If you don't mind, we'll switch to Adrian now for a few minutes, and then we'll come back with questions. So, Adrian, over to you.
Thomas, I shall share my screen now. Everybody should see this in just one moment. Is that visible, Thomas? Great. So, first of all, thank you very much to Thomas about this talk. I'd just like to say a few words about the micromaterials, nano and microscale reliability testing techniques we can offer. Some of you are familiar with the testing instruments we make here at Micromaterials, so a multifunctional mechanical characterization tool. I'd just like to focus on these three functions today, so nano and microstructure wear, nano pressing, and nano fiber test. So why do we do nano and micro scale tribology work? Well, as you're all well aware, if we take two sliding surfaces face to face, in actual fact, our nominal contact area actually comprises many millions of small asperity contacts, at which there are very, very high localized pressures. And it's these localized high pressure points which often lead to the onset of a tribological failure. So if we can use a very small probe in a scratch test or a wear test to simulate one of these asperity contacts, we can start to learn a bit about the fundamental origin of tribo failure. What do we control or measure in nano and microscale tribology tests? Well, we can control the contact pressure by controlling load and contact geometry. We can control how we apply the load. We can ramp it or have it constant. We can control sliding velocity, we can control sliding distance, we can change the material pair that are sliding. Often we use a diamond probe, but that isn't fixed. We could use a steel probe or whatever material you wanted to use. And we can change the environment. As we've just seen, environment is very important in tribo systems. We measure usually the depth of the probe into the material, so we get a view of the total deformation, also plastic deformation itself, friction acting on the test probe, acoustic emission, and electrical current flow are other things that we can monitor in addition to these standard metrics. So 3 techniques: nano scratch, nano fretting, and nano tribo test. As I said, they cover a range of contact conditions. So we're trying to encompass as many real world type scenarios as possible. So there's a summary here of how they compare. But basically, nano scratch tends to be a single pass test over a short distance. And at the other end of the scale, the nano tribo test offers us many passes over a longer distance. Okay, and the nano fretting is in between those two. So scratch and wear testing, typically what we do is we do a profile of the sample surface. So here's our surface roughness. So this is depth versus distance. Then we apply our scratch load. So we scan along, we return to the beginning, we apply our scratch load. At a certain point, the depth suddenly increases. Something's happened. We don't know what's happened at this point, but our instrument tells us something's happened. We then do another topography along the scratch path, and we see this big step here, which we saw no evidence of in our loaded pass. So what this is telling us straight away is there's some kind of tensile failure that's taking place in this coating of substrate system. So that's an adhesive failure. And as we just saw, adhesion of coatings is very important. So here's the corresponding microscopy, and you can see this delaminated region. So as well as depth, we also measure friction. And friction can be very useful as it can give us an earlier indication of early stages of failure. Nano fretting works over a much shorter scan distance usually. It's in between AFM and conventional tribometers. So we can actually cross the boundary from static to sliding friction in with this test. As you can see, some work actually I think that was done here at Southampton University. We can actually extract even micron scale friction loops from this test as well. So here's some example work on some biomedical alloys, and really what we're looking at here is the evolution of these fretting damage that takes place in these materials at various different contact loads. So the contact geometry is the same in all cases, but as you can see, the way in which the debris at that interface evolves differs between the materials. So one thing that may look very good at a low level of loading may not be quite so good at a higher level of loading. In terms of instrumented test data, what we tend to look at is displacement here, which means depth of the probe into the sample as a function of time or as a function of cycle number. And what tends to typify or give us an indication that a failure has occurred is a sudden increase in the depth. So here we see an increase of about 1.5 microns. This is a 1 micron coating on a silicon wafer. So there's a very clear failure event taking place here. The nano-tribo test, as with all of these techniques, utilizes the same nanotest loading head as all of our testing methodologies. And essentially, it's a linear reciprocating tribometer test. The sample is oscillated backwards and forwards over a user-specified distance, can be up to 40 millimeters. Friction's measured continuously, and we can measure depth data as well. So we can change the contact geometry. It's very flexible. So in this case, we've got a very big 6 millimeter diameter ball in place. So here's some example data. Again, our familiar kind of reciprocating tribometer friction versus sliding distance charts. We can convert our friction data into frictionally dissipated energy per cycle. And we can see with these particular systems, about 40 cycles at a pretty constant level of dissipation, then a ramp up, which signifies some significant change in that tribo system, possibly the onset of a complete failure. So that's just very, very quick overview of the things we can do there. As I said, we can combine these things with environmental control as well. So more information is available on our website, and of course, do feel free to contact me directly, and I can try to give you more examples that may be specific to your applications. Thanks very much.
Thank you, Adrian. That was you. So perhaps we'll come back to questions, Andre, if you don't mind. There are some beautiful comments on the site, and lots of appreciation of your talk. So thank you for that. I hope you can hear us, Andrew. So I'll go for some questions. So Zach is asking if you have any thoughts on developing coatings on soft polymer substrates. So I guess first of all, in terms of processing temperature, wherever that possible, and then perhaps if you could comment on performance on polymer substrates. We cannot hear you, Andre. So it seems like we lost Andre, which is a shame. Maybe we'll give him a few seconds to join. I appreciate we just passed 1 hour of this webinar, so we are running slightly over. So apologies for that, but we hope to take a few questions and give Andre an opportunity to comment. But it seems like Andre is not online anymore. There has to be a technical problem. I cannot see him on the attendees list of attendees. So my apologies for that. We'll need to follow this up in other way. So thanks to Andre, thanks for MML for supporting this event, and thank you all for joining and for questions. It's much appreciated. Just a reminder that you will receive a link to recording of that video automatically sent by Daniel platform shortly after the event. And we'll organize the next webinar in a few weeks towards end of July, so please stay tuned. So see you next time, but for now, thanks for joining, much appreciated, and enjoy the rest of your day. Thank you. Bye.